Today we're going to look at torque on a current loop, which is the essential feature of electric motors. Then we're also going to look at how they first measured the ratio of the charge to the mass on the electron, which is a lab we're going to do later on. So starting out with torque on a loop. So if we imagine that we have a loop, and we're going to make it pretty much square here just because the calculations are a little bit easier, but our answer is going to apply to a loop of any shape really. So if we have this loop in a magnetic field and we've got a current going clockwise around this loop, then on this branch of our loop we've got I cross B, and if we point our fingers that way, our palm that way, then our thumb will point into the page. On the other side the current's coming the other direction, so the force will be coming out of the page. If we look from the bird's eye view, so same magnetic field here, but the current is coming up this wire, so that's the bird's eye view, and down that wire, we see that we have two forces of equal magnitude, opposite directions. So the net force would actually be zero, though we have a torque acting on this loop that will cause the loop to spin at least a little bit. Once it gets to this orientation here, then there will no longer be a torque because these forces will just be pulling in that direction. But for a while we can get it to spin. And if we get enough momentum, we can overshoot that, and what electric motors do is they switch the direction after that to keep it going. But anyway, at some other point midway between, you would still have some torque, but it will be reduced a bit. And we'll come back later to this idea of a vector coming out of the face here. First of all, let's figure out an expression for the torque. If I look at the force on one of the wires, so one side, not sine, that's going to be I times A, because this length here is A. This is just ILB. It's perpendicular, so the sine theta becomes 1. And then if I'm looking at the torque on this loop, I'm going to have the torque on one side, which is force, IAB, times the lever arm, which is this distance here. That total distance is lowercase b, so we've got b over 2. And that's for one side. On the other side, even though the force is in the opposite direction, it will cause it to rotate the same direction, so we're going to add those torques together. IA big B times little b over 2, and those sum to give us I. I'm going to put the A and the little b in between here. This here, A times B, is just the area inside that loop, so this becomes I capital A, area of the loop, times the magnetic field. Now this is for a single loop of wire, so one loop, and often if you have an electric motor you're going to have a whole coil of wires, so in that case the torque would be the same expression but times the number of loops that you have, the number of coils you have. Okay, now that's going to be the maximum torque at this location here. When it starts rotating, you're only going to get a component of that, so this will become the more general form, NIAB. I guess you could call this the max torque here. This is going to be a NIAB sine theta. Alright, and here it is written a little more nicely. Now this NIA part, we call that the magnetic dipole moment, and that's essentially the contribution due to the loop, and then this is the B field and the orientation part. So moving right along, we have this as what I just mentioned, the magnetic dipole moment. We describe it as a vector quantity with A being the area vector. It has magnitude equal to the area of the loop, and the direction is perpendicular out of the face. So this theta here is between these two vectors, the vector coming perpendicular to the face of our coil and the vector of the magnetic field. Excuse me. So we can write this a little more succinctly. We can say that the torque is NIA cross B rather than NIAB sine theta. And since this vector thing here is NIA, we can just say that the torque is the magnetic dipole moment crossed with the magnetic field. So not really any new ideas, just a different way of writing it. Now we can also define the potential energy of this loop, because if we let it go, it will start rotating. in general, the potential energy, if you're looking at a linear system, it's F dx, but in a rotational sense, we do torque d theta. So we can go ahead and plug in our torque, which is NIAB sine theta, and all of that is d theta. This works out to be, if we substitute in this guy, the magnetic dipole moment, we're going to have mu times b times cosine of theta. We've got a negative sign there. And we did the indefinite integral, so we have plus c. But whenever we're dealing with potential energies, we can set potential energy equal to 0 wherever we want. So we often choose the potential energy to be 0 when theta is equal to 90 degrees. And if that's the case, then c will equal 0. So that gives us this nice expression here, which we can write as the dot product, because whenever you have two magnitudes and the cosine of the angle between them, that's the dot product. Now if you think about this definition here, this is actually kind of a strange way to define it. We're saying as 0 potential energy when we are at 90 degrees, so that is this situation right here. So we're saying this is 0 potential energy. But that's when we have the maximum torque. That's actually the maximum potential energy. When it rotates here, then we're going to say that we have negative potential energy according to this expression here. So essentially we went from 0 potential energy to some negative potential energy. So this is still the maximum energy configuration regardless of how we define the 0 potential energy location. It just works out to be easier to do some calculations if we define it this way. Alright, moving on to the charge to mass ratio. You've probably seen this a bit in chemistry, but it actually takes an electric field and a magnetic field and some basic understanding of how those things work on charged particles to figure out the charge to mass ratio. So if we have a setup like this, essentially we have some source of electrons. A lot of times you just have a wire that gets hot by having a current run through it, and it will start just ejecting electrons in all directions. And then if you set up an electric field like between a positive and negative plates, that's going to accelerate those electrons. This is just going to focus them in a given direction. Now here I've got some plates that I can charge, and then I've got some loops that I can use to create a magnetic field. If the current is going this way, if you remember one of the many right-hand rules, if you curl your fingers in that direction, it's going to create a magnetic field into the page. So I'll draw some X's here. Our magnetic field goes that way. And if initially we don't have these plates charged at all we have is a magnetic field, and then we think about what the path of the electrons is going to be. They're going to move this way, so we're going to do V to the right, cross B, so you put your palm into the page, so that will be an upward force on positive particles, which means it's a downward force on the electrons. So the electrons will end up over here if there is just a magnetic field. And we can describe that curve by setting the magnetic force, which is EVB, equal to the centripetal force, as we saw earlier, so mv squared over r. Cancel out one of the v's, and we'll solve for the charge to mass ratio of v over br. So we can measure r and we can measure b, but it's going to be difficult to know the velocities coming out of this, even though we focus them in one direction. And even though we accelerated them through a given potential, some of them might have had more energy or less energy coming off of whatever was spewing the electrons. So we're not really sure just by looking at the deflection in a magnetic field what the charge to mass ratio is. But if we then turn on the E field and we get a voltage selector, or sorry, a velocity selector, so we turn on just enough E field to get our electrons going in a straight line. So this is where they go if there's only magnetic field, then they'll go straight here if we have electric and magnetic field of just the right magnitudes. If you remember in the previous video we said that the velocity is going to be the ratio of the electric field to the magnetic field. So this is going to allow us to get the velocity of those electrons. We can go ahead and plug that into this equation here. So we're going to get E over B, and that B will combine with this one. So if we run the experiment like this, we can measure the E field and the B field in R, and this gives us the charge to mass ratio on the electron. Unfortunately, it doesn't give us one or the other. We would have to find one and then we could find the other, but for now we just know the ratio. The way that the charge on the electron was actually figured out was with another experiment called the Milliken oil drop experiment. So he used an atomizer, which is kind of like an old-fashioned perfume bottle, and what that does is it ionizes a lot of these oil particles, these oil droplets, and then he had them fall through this apparatus here where you have some charged plates. And first of all, he found the terminal velocity of these particles, and from the terminal velocity, figuring out the drag force, he was able to figure out the mass of these droplets. Now that's not the mass on the electron, it's just the mass of the droplet. And then he turned on this electric field and levitated the particles such that the electric force acting on them was equal to the weight of the particle. So if we want to find the charge on each droplet, it's equal to mg over E. Now they could measure E by looking at the voltage they applied to these plates. The mass, I told you, they already got from looking at the terminal velocities of these droplets. And so this allowed them to find the charge on each droplet. Again, this isn't the charge on a single electron, but what they found was whenever they found the charge on these droplets, then they found it was a multiple of some number that is the elementary charge. So this is how they figured out the charge on the electron. Then they could go back and plug that into the charge to mass ratio and get the mass on the electron. And the values that they found in this very first experiment were pretty close to those accepted today.